You know, like it's so easy to put it in rectangular form. Can I just do that? Absolutely. If the directions are just saying find the derivative, dy dx specifically, I don't care how you do it short of cheating. So any way you want. And I'll show you some examples in a couple minutes. This one is a little funkier because it's kind of like, well, can I just take the derivative of whatever I get as an answer here? Well, not really. Right? Oh, and the one condition here, dx dt has to be something non-zero, because if you're following this relationship, if dx dt is equal to 0, you're looking at an undefined relationship. All right, I just figured I'd mention that because it comes up again here. So we're looking for the derivative with respect to x of dy dx. Sorry. So we're looking for the derivative of this y. All right. And so see the best way to explain. I think I've already, because I took the time to type it, it's all pretty much there. I just want to say it the right way. Okay, well, I don't think there's anything else to say. I was going to elaborate, but it's all like right. Yeah.
Is that double derivative or?
The second derivative. Yeah. So you're taking, because it's based on the notation, but really it's the idea that you're taking the second derivative of y, but the rate of change is per x per x. So we would still need a dx dt as a divisor. And that's the thing that people lose sight of. So we're taking the derivative with respect to t of the dy dx function, and then from there we're going to divide by the dx dt. I think I'll do an example first on this, and then come back to the arc length stuff, because I want to flesh out why this formula works the way it does a little bit more. But I don't think it's going to make as much sense until we see it in action. On both ways with this. Let me just, sorry. I just don't want to have to flip pages back and forth to point at it. There we go. That looks nice. All right, so let me just make sure. Angela, so this is corresponding to that. So these are our rules. I'm just tucking it in the corner here. So we're looking for dy dx and then the second derivative. All right, so dy dx again, dy dt divided by dx dt. So dy dt based off of this guy here would be 6t minus 2 plus dx dt would be equal to, I can just rewrite this, 2t to the 1/2. So t to the negative 1/2 power. All right. So if I'm looking for dy dx, I'm just dividing these two things. The ratio of dy dt and dx dt All right. So then, so that's our first derivative. Now our second derivative is where, in essence, what we're doing is we're actually following the same process a second time. And so that's hopefully going to explain why this formula works the way it does. I think this is probably the best way to do it. So if I'm just going back to my first derivative rule, which would be dy dx is equal to dy dt over dx dt. All right. Again, I'm finding the second derivative here. Right. I am, in fact, finding the derivative of my derivative. So with respect to x. So that would be the same as saying replace my y's with the thing I'm trying to find the derivative of. That thing that I'm trying to find the derivative of is the first derivative, dy dx. Because I'm finding the derivative of this new y, dy dx, with respect to x. Right? Following the same process, it really just amounts to taking the derivative on the top of this expression here. So I need to differentiate this. So, I mean, you may want to clean it up first a little bit. Right? Because otherwise you got some quotient rule in there. Might be a little funky. But if you multiply top and bottom by t to the 1/2 power, you get 6t to the 3/2 minus 2t to the 1/2. All right, so I'm multiplying each part on the top by t to the 1/2 power. All right, which is, I mean, you could think of it either way. You could just look at it as multiplying by the reciprocal, a little keep change flip, because this is really the same as saying 1 over t to the 1/2. Or I could just say I'm correcting for that by multiplying top and bottom by t to the 1/2. If I multiply the bottom by t to the 1/2, it's going to cancel out. On the top, it would have to be distributed to each one of these. That t has a power of 1. When I multiply it by t to the 1/2, 1 plus 1/2 gives me the 3/2. The benefit of doing the simplification here, even though you were not instructed to, is because you have to find a second derivative. I prefer power rule. I mean, I think we all do, to anything other than that. Right? So if you have a choice between power rule and literally any other type of differentiating, it's going to be power rule. All right. So what is that? 9t to the 1/2. Yeah. Minus t to the negative 1/2. And then the bottom is dx dt. We already have that. Right? We figured it out over here. So t to the negative first. And this you would not need to simplify if you didn't want to, but you might be just drawn to the idea of simplifying it because it's going to clean up. You're going to get 9t minus a 1. Right. Which is shockingly simple. Not the process, of course. The process is elaborate. But the answer, 9t minus 1. To think that the rate of change of the rate of change would actually be some simple linear relationship. Interesting. So the next example is really just asking you to do the same thing, at least in terms of the first derivative. It's just it's asking you to find the equation of the tangent line. So something that needs to be reviewed, because even though it comes up over and over and over again, it tends to be the first thing that goes out the window when people move from course to course. You remember product quotient chain rule for derivatives. You remember things like integration by parts. That's about it from Calc 2. And then, yeah, tangent line. There's just no place for it. Yeah, so we have to reinvestigate that. All right. The tangent line is a rectangular equation. Y equals m times x minus x sub 1 plus y sub 1. All right. It's the point slope form of a linear function. You might know it as y minus y sub 1 equals m times x minus x sub 1. So basically this y sub 1 on the other side. But I think that's stupid. Like, why is that over there? It makes perfect sense to be on the other side, especially since every other function has a standard form that follows this model. Like if you wanted the quadratic standard form, just throw a power of 2 on this bad boy and you have it. Power of 3, yeah, throw a log out in front of it and you have the standard form for a logarithm. So this is a perfect standard form, even though it's not called the standard form for a linear function for some reason. It's the perfect standard form for it. All right, that m, it has been and always will be dy dx. x1 and y1 are some particular coordinate on the graph. All right, so they're telling us to come up with this tangent line equation specifically at the point where t is equal to 3 pi over 4. Right? So that would have, well, the first thing I would need to do, I mean, we don't need a graph necessarily. You're welcome to it, and I'll show you how a graph can be a good support for a question like this. But I do need the x and y values that go along with that t value. So I'll make a little mini table, very mini. 3 pi over 4. So the x value comes from whatever 4 times the cosine of your t value is. All right. So that requires you to know something about the unit circle. So 4 times, I mean, it's a little too early in the semester for I told you so. But you do need to know the unit circle. Because this question could very easily say, answer will only be accepted in exact form. Now, there's ways around it. You can wiggle your way around not knowing the unit circle, but life is just so much easier if you do. All right. So the cosine of 3 pi over 4, if you please. Negative rad 2 over 2. Very good. All right. The sine of 3 pi over 4. Rad 2 over 2. Everybody knew that. Yes. Everybody. If you need a refresher on the unit circle and how to create it and what its uses are, let's go to my YouTube channel and type in unit circle. There's a click subscribe and smash that bell icon for notifications and what's that, the thumbs up for everything. Just keep thumbing it up. Log into different accounts just to hit thumbs up. Yeah, anything. There's no way for me to keep track of it, unfortunately. I mean, I give you the points for actually subscribing to my YouTube channel, but I don't think I can give it to you for multiple accounts because what's to stop a person from creating like 300 accounts and getting 300 bonus points and just saying, yeah, I'm not even going to take a test, like I'm good. You know? I mean, it's a good strategy. I just can't. So negative 2 rad 2. And, well, the other one is just 3 halves rad 2. So 3 halves rad 2. All right, so we have some x and y values. So all the pre-calc stuff's out the way. The pre-calc class that may or may not have taught anything about this stuff. So I know that's the frustrating thing, but somehow you're supposed to know. Anyway, but we do need the slope. All right, the slope should be easy to come by because I need, again, dy dt. Then I need dx dt. Do the y first, then the x, because it'll give you the nice ratio and be ready to rock and roll. So the derivative of 3 sine t with respect to t would be what? 3 cosine t, yep. And the derivative of 4 cosine t? Negative 4 sine t. If you're interested in playing around with GeoGebra, at some point you're going to be required to. It's not going to be a matter of being interested. It's going to be a matter of you got to do it, so do it. For some reason, I mean, I think it's a pretty good reason, but GeoGebra doesn't understand when you type in COST because it thinks you're writing cost. So anytime you put in a trig function, you have to put a set of parentheses to account for whatever the argument is, regardless of whether it's a simple t or t minus 1 or whatever. Always parentheses around it. It'll save you some aggravation later on. You could tell I've been aggravated by that. So this is happening at t equals 3 pi over 4. So what I need is little notation action here for you. dy dt when t is equal to 3 pi over 4. And I also need dx dt when t is equal to 3 pi over 4. All right. The good news is we've kind of already answered this because it's the same trig ratios and it's the same reference angle. So we're going to get a lot of the same stuff. Right? So negative root 2 over 2 multiplied by 3. So negative 3/2 root 2. And then positive root 2 over 2 multiplied by negative 4. So we're looking at, well, the same thing, negative 2 root 2. All right. So what we have to do in order to find dy dx at this location at t equals 3 pi over 4 would be just to divide these two things. All right, because you could, if you want, divide your derivatives and get negative 3/4 cotangent t. But if you don't know the unit circle ratios for cosine and sine, my faith in your knowledge of cotangent, tangent, secant, and cosecant is somewhat limited. Okay, question.
Wasn't the dy dt supposed to be positive? When you wrote it the second time?
The second time. Oh, here?
Yeah. Because you wrote it was positive when you wrote it in purple.
Right, but the ratio ends up being negative.
Oh.
When you pop it in, it gives you negative root 2 over 2 at 3 pi over 4. All right, so then when you simplify, the root 2's are going to go away. This is really a negative 2 over 1. So you're looking at 3/4. Again, calculator can support you on this. Depending on the directions, it may even do all the work for you. So just be always mindful of what the question is asking you to do. I'm not in the business of making you do like a ton of work on a test. That's not the point. There's always some shortcut to getting the job done. I mean, and I sometimes I feel bad about it, but I've done this before. I gave a test in my high school Calc class where it was find the derivative. I almost fell. Find the derivative of cosine squared of the natural log of x plus sine squared of the natural log of x, where x has to be greater than or equal to 7. And the amount of work I saw from that for that problem was like astronomical. But the savvy student just put down 0 and called it a day because it was cosine squared plus sine squared. That's an identity. Cosine squared plus sine squared is equal to 1. The derivative of 1 is equal to 0. Done. You know, so it was a way of separating out people of like, who are the people who really know what they need to know and who are the folks that are, you know, just going to blindly follow steps, right? So there will be some questions like that, but then there will also be questions, when I show you in a second, like this, where you could just crank it out on the calculator and call it a day, right? So there's a fair amount of work here if you have to do it by hand, but you're not always going to have to do it by hand, right? End of speech. You're all sufficiently motivated. So y equals 3 over 4 times x minus, we discovered x was the negative 2 rad 2, so it would become plus 2 rad 2 plus the y value of 3/2 radical 2. That's disgusting. Look at that. No, it's great. It's great. It'll be even better when you actually get a sense of why on earth we're learning any of this. That's part of the fun. But yeah, you could, But the point slope form for a linear function is the most beneficial way to have an equation of a line represented because it tells you everything you need to know. You have a point and you have a slope. For a line, that's all you need. So if you distribute it out, you would get a y-intercept and a slope, but you're not in any better of a position. So this is fine. So you're welcome to simplify it, but again, at your own risk. All right, that's something to always keep in mind.
You got y1 points from the little chart we did on the left.
From the little chart that ended up not looking much like a chart, yeah. All right, so to the calculator, to the Hinton feeder. Less. So xy. The x was 4 cosine. Calculator builds in the parentheses, so at least we don't have to worry about that. 3 times the sine of t. All right, I'll just do a standard zoom. All right, that is the calculator drawing an ellipse. And it's also a shot to my pride because it's yet another thing that can draw an ellipse better than I can, and even it couldn't do much of a good job. Benefit of parametric mode is that things that are not functions in a rectangular coordinate system, they don't pass the vertical line test, they don't cause problems for us in parametric form. Right? You'll see some crazy looking graphs in parametric form that you'd have no hope of being able to create in function mode. Right. So, and then that would beg the question of if I needed to graph this on that, how would I do it? And I'll get into that in a minute. But what I want now is to somehow come up with these numbers, or at least approximations of these numbers, using the calculator. So, not by having to do anything out by hand. So I've already talked about the menu. Second, trace. Go to value first to get your x and y's. You can go to the table if you want, but unless you want to play around with the table settings so that you can get it to go in increments of pi, or in this case, pi over 4, probably not the best way to go. So select value, put in your 3 pi over 4, and hit enter. You get those nasty decimals. Second, trace option 1. I'll do it again.
How did you get to have the T like the T without editing it?
Like when I did the value?
No, when you got the window and the ellipse showed up.
Oh, I just did zoom 6. Just rocked a standard zoom. Doesn't always work, but in this case, well, I also kind of cheated based on my extensive knowledge of conic sections. Also, you might have done this too, because if you looked at this and you say, oh, hey, this is what we did on the previous page, or 2 pages ago. That was the ellipse, and that meant that you're going to go out like 3 or 4 in each direction. So negative 10 to 10 should cover you there, right? So you can do that. But standard zoom is a good place to start. If you don't have a sense at all of what the window ought to be, bless you, go into your table, take a look at the types of numbers that you see there, and then build your window off of that. So second, trace value, 3 pi over 4, hit enter. So it's going to report back an x value and a y value. They're not at all in the form that we want, but we know that they're going to be equivalent to these numbers somehow. So let's quit out of here. In my home screen, if I were to select X, so right above store. Now, you don't want to hit this key that you would usually hit for X, because we're in parametric mode. It's not going to bring up an X, it's going to bring up a T. So you have to do it the old-fashioned way. So alpha, hit the store key, brings up X. That number that came up from the value has been stored in as X. And if I select Y, alpha 1, the number that came up as Y has been stored in. So I can manipulate these numbers now. Right? I don't have to go back and forth to the graph. So then if your thought process is, oh, I got to do trial and error now, that sucks. No, if you figure it's the square root of something, that's a place to start. It's the square root of 4.5. Now we're closer to being exact. Math bracket, if you somehow don't know what 4.5 is in fraction form, that's not meant to sound like an insult. It just did sound like an insult. But 4.5, I mean, you should, you should know. That's not halves. No. So, worst case scenario, well, that's why I go over it. Worst case scenario, you hit math, enter, enter, to convert it over into fraction form. All right? So, I mean, if you're coming from an environment where use of calculator was discouraged completely, this is like I'm throwing a ton of stuff at you. You're like, how am I supposed to learn all this on like one night? We'll be reviewing this repeatedly throughout the course, but you got to understand, there's folks in here that have been doing this for a while, you know. So that's the thing. It all depends on where you've been coming from. So if you're a novice with it, there is a learning curve. But if you've been using it for a while, this is an old hat. It's just adjusting your thinking to parametric form rather than function form. So I took whatever that decimal was and I squared it. So that means that whatever I had is the equivalent to the square root of 9/2. Now you could simplify it the rest of the way. 3 over root 2. If you rationalize that, you get this. Okay? Radicals and bottoms of fractions are not a problem. All right? So if I wrote this as 3 over root 2 instead of 3/2 radical 2, I'm not losing any credit for that. There was never anything wrong with having a radical in the bottom of a fraction. It was all a lie. It's sad. They lied to you. All right, the x, square that. Ah, that's even nicer. So it's got to be the root of this. So the square root of 8. Simplify to root 2. But it was negative, so I don't want to lose sight of that. So so this would replace this if I needed it to. This I'd get naturally. The only question would be, all right, cool, I can get coordinates using the calculator. That's awesome. What about the calculus? Again, second trace, you have 3 different types of derivatives in here. I can calculator my way to coming up with these particular derivatives and also the overall dy dx at t equals 3 pi over 2. And why this thing keeps shrinking on me, I have no idea, and it's really frosting me. Option 2. With a stormtrooper on my shirt too, so it's like a big knife. So dy dx, type in the 3 pi over 2, 3 pi over 4, and you get 0.75. So if I offended you deeply with my 4.5 earlier, hopefully I won't also offend you by saying I think it should be pretty obvious that 0.75 is equivalent to the fraction 3 over 4. That part we're good.
Can you repeat what you did because I'm not getting it.
Second trace.
Second trace.
dy dx option 2. And type in the 3 pi over 4. This one is weird because it doesn't give you a field of t equals. So you just have to know. That's annoying, but you just have to know to type. To just start typing, and a t equals will magically appear. 3 pi over 4. Hit enter, and then you should have it. All right. And that's the same in the function mode. If you use the dy dx feature, it doesn't say input this number here. You have to know to do it.
So let's say on a quiz or whatever, we can just tear through this, writing everything out, or we can plug it into the calculator and say, oh, it's 3/4, and I'm done.
Correct.
Like a just big 3/4, there's nothing else on the paper.
Just watch the directions. If they say show all work, like only an analytic solution will be accepted. That's the key term or phrase to say I need all this stuff. But if I've had people get confused by this, so it's very important that you understand. Show all work written on the top of a test. I think pretty much every math teacher that ever lived has written show all work or some phrase for related to that on top of their test. but what it means to that individual is always going to be different. So for me, if a calculator approach is going to be used, show all work means give me the answer, tell me what you did in the calculator. All right, so don't say just 3/4. It might sound lame. Say 3/4. I used second trace.
Oh, so you don't have to do the work. You can actually say,
right.
This is these steps. These are the steps I do with the calculator.
Correct. But I don't need the button for button steps. and the reason why, and honestly, I don't even really need that. It's just I've had enough situations where for like a 5-point question, but a calculator approach is perfectly fine. Person puts down the answer. They're pretty confident about it. Unfortunately, they probably shouldn't have been because it's wrong, and I have no way to give partial credit. So give me the answer and give me something along with it. Sometimes a quick sketch. You know, I mean, I don't know that necessarily makes sense in this case, but sometimes, you know, a quick sketch will get it done. A brief description of what you did in the calculator. Very brief. I don't have much of an attention span when I'm grading. Some of you at some point will witness me grading. I tear through grading. Like you'll never have to wait long to get papers back because that's not my style. I like to get it done. And so if a person has a simple explanation that gets the job done, boom, full credit. When I see like the narrative, I'm like, ah, crap. All right, put that to the bottom of the pile. I got to read that? Jeez. Yeah, I'm not interested in that. All right, so simple. That's what I'm looking for. So once I recognize in the graph that it said X, so I'll just do it real quick. When I did the value, I typed in the 3 pi over 4. So these came up. You have to take note of what variables are used here. In this case, X and Y. So it's not really as much copying as it is recalling what has been stored, because you're just looking for the X key on your calculator. So it would be alpha store to bring up X. And since that value has been stored in as X, it would come up when you hit enter. And the same thing for Y. So alpha 1 to bring up the Y. 21st century, you would think it would have a copy-paste feature by now, but it does not. It does not. In fact, this calculator has barely changed in the 20 years I've been teaching. Find all points of horizontal and vertical tangent given the parametric equations. That gets a nice, juicy star so that you can tackle that one on your own.